So today I'm gonna be talking about unlimited non-causal correlations in the relation to non-locality. What does this mean? So what is non-locality? What is non-causality? So we're gonna have a look at all of these things in the talk and like try to understand what is all the like what does this all mean and how are they related? So we'll first discuss non-locality, and there's another notion of no signaling, and then we'll see that is there any connection which achieves both both no signaling and non-locality, and like what is the connection between the two, and like analogously, we'll see what is non-causality and what is logical consistency, and there any correlation which achieves both. Um, and again, as you may observe, like by the end of the talk, that these two ideas are analogous. So let's first start um, with with notation and like what are we gonna assume, what are we gonna use. So naturally we're gonna use uppercase letters for random variables and lowercase letters for instances of random variables. If you're assigning it some value, then we'll use lowercase letters. We assume that the parties receive binary inputs and binary outputs, that is 0, 1 are the possible inputs and 0, 1 are the possible outputs for each of the parties. And if we have like two parties, we'll call it Alice and Bob. If we have three, we'll call it Alice, Bob, and Charlie. And the inputs of the parties will denote by the random variables X, Y, and Z, if there's a third party. And the outputs will denote by A, B, and C. You can see the picture on the right side for the two-party case. And if in case we have multiple parties, will denote the respective input and output of the kth party by xk and the output of the kth party by ak. So let's first discuss what is locality. Before we look at non-locality, it is extremely important to understand what is locality. Um, so if Alice and Bob are two parties in the like easiest setup, and and if we don't and like a correlation is local, if Alice's output bit is independent of Bob's input bit and vice versa. So they're working in the local setup, and we can have and like probabilistically we can write that the joint distribution of Alice and Bob is like a convex combination of the independent distributions of Alice and Bob, and there's a convex combination because we are allowing for shared randomness, so they can have shared coin tosses results with them, and they can use that. So that's why we're allowing this convex combination. So if we assume that there are n parties, how do we generalize this setup? So this idea generalizes very naturally, and we can say that all the parties are working in their respective local setting, um, and like the probabilities are like a convex combination of the of the marginal probabilities. And so by its name, a correlation is non-local if it is not local. So there are a few examples of locality and non-locality. So let us see a few correlations and answer like whether these correlations are local or non-local. Um, so if you have something like the XOR of the outputs is equal to the you can think of these correlations as like games that we want to satisfy these conditions. That the XOR of the outputs of Alice and Bob is equal to the XOR of the inputs. So is there any strategy such that Alice and Bob can win their game locally, like without doing any communication, without having any correlation between them? Yes, for the first correlation, yes, there's a very trivial strategy that Alice outputs her own bit X and Bob outputs her own bit Y. So A equals to X and B equals to Y, and then therefore the XOR of A and B is equal to XOR of X and Y. So this correlation is local. What about this one? If we want the XOR of the outputs equal to the end of the inputs, is this local? Can we achieve this locally? Well, I guess not, because there is no such strategy that Alice would output something and Bob would output something using only X and Y. And if we XOR the results, we get X dot Y. That is not possible. You can check that out. And actually, the winning probability of this correlation is 3 over 4. It's a good idea to work through it. It's called the PR box. It's a very, very, very famous correlation in non-locality. And so what about this one? If we have like the XOR, if we have like n parties and we want the XOR of the outputs to be equal to 1 XOR with the XOR of the inputs. Well, this seems to be a little bit towards non-local, but I guess it is local. Like one particular strategy would be for the first party to output um, the negation of the input, which would account for this one, um, and then all of the other parties would output the inputs. So then, if we XOR all of those, we get one XOR all of the inputs. So this is also local. And so what about this one? This is a very important correlation in the study of non-locality. It is called the Ardehali-Svetlichny correlation. And so does there exist a local strategy to achieve this correlation? Well, similar to the reasoning we provided for the second one, this is also non-local. And we'll see later that this correlation is actually can only be this correlation can only be simulated locally with probability half. So let us now turn to the very important concept of bilocality. What do we mean by that? So what do we do is we take the set of parties and we partition it into two sets, P1 and P2. And if any correlation can be simulated by like any partition of the parties, it is called bilocal. So for example, if we have like these two partitions where the one, third, fourth, and seventh parties are in the first partition and the other three parties are in the second partition, um, then uh, if any correlation can be simulated with this setting, then that correlation is bilocal. And there's another very important idea of genuine non-locality. If a correlation cannot be bilocal, because bilocality is the strongest locality that we can have. So if a correlation cannot even be bilocal, then it has to be genuinely non-local. So let us again see a few examples of when like if we can distinguish bilocality and genuine non-locality. So if you have some condition of a game like the one stated here, and if we want to win this game, does there exist a bilocal strategy? Does there exist a bipartition such that uh, such that we can win this game? Well, yes. For the first one, there does exist a bipartition. It is easy to see that if we allow Alice and Bob to be in the same partition, then then they can communicate with each other, and uh, and then they can like produce X dot Y, and the third party Charlie would output zero. So the output so the XOR of the outputs would be equal to X dot Y. What about this one? This correlation we saw earlier is a special case of a correlation we saw earlier. And so this is actually a local correlation. So will it be bilocal? Yes. Every local correlation has to be bilocal, because we can have any partitions and we can allow communication in between the partitions. But it's the party's choice to not communicate and work locally. So we can simulate any local correlation using bilocality. And so what about this one? We saw this correlation earlier too, the Ardehali-Svetlichny correlation. It turns out that this correlation is not even bilocal. So there does not exist a partition such that we divide the parties into two parts, and we allow communication in between parts, but both parts are not allowed to communicate with each other. So interpartition communication is allowed. Sorry, intra-partition communication is allowed. Interpartition communication is not allowed. So we cannot have any such partition such that we can always win this game with the given condition. So let us now look at the no signaling principle. What do we mean by that? We stated that in the first slide, but what do we mean by that? Let's look at it in a little bit detail. So correlation is no signaling. Um, if like some parties are sharing it, they're not allowed to communicate using that correlation. So they may communicate to generate that correlation, but once they share that correlation, there can't be any communication between any disjoint subset of the parties. So let's see an example for two parties. We can have like we can explicitly state the conditions for no signaling as follows. So the first expression in the first equation, we're simply saying that if Bob changes its input bit y to y bar, it does not affect Alice's probability distribution. That means that the Alice will not be. This means that Bob will not be able to signal um, anything to Alice because the Alice's probability distribution is independent of Bob's probability distributions. In particular, we mean that if Bob changes y to y bar, um, Alice cannot get any information. So Bob can't communicate with Alice using this correlation. And similarly, the second condition is for Alice to be not able to signal to Bob. Uh, so this is like bidirection. Both Alice and Bob can't communicate with each other. And so if we look at a third party, at a like a three-party example, it is like difficult to it's not difficult as such, but it's like tedious to like work out all the conditions for a correlation to be non-signaling. But we can have a diagram like this which just says that Alice and Bob can't communicate, Alice and Charlie can't communicate, or like any disjoint subset of the parties can communicate. For example, Alice and Charlie, the joint system of Alice and Charlie is not allowed to communicate with Bob. So there are a few examples of no signaling. What do you think about this one? Is the OR of the outputs. So we want to satisfy this condition, and like you can assume that Alice and Bob are given some inputs, and they're given some correlation. They're given some kind of a box in which they input the input bits, and they'll get some they'll get some outputs, um, which will satisfy this condition. So in that case, will Alice be able to signal to Bob, or will Bob be able to signal to Alice? Well, I guess yes, because if Alice chooses her input bit to be zero, um, then this end of x and y will be zero, and the OR of a and b has to be zero. But the OR is only zero when both a and b are zero, so b will also have to be zero. This means that if Alice chooses x to be zero, then it is guaranteed that the output of Bob will be zero. So this means that there is like Alice is able to signal something to Bob by changing her input. And so we also know, we'll not show this, but we also know that every correlation of this form, which is also called an XOR correlation or an XOR game in the literature of non-locality, is no signaling. It just says that the output, that the XOR of the outputs is equal to some function of the inputs. And so what is the connection between locality and no signaling? Like we discussed these ideas, but what is actually the connection between those? So we can easily see that every local correlation is no signaling. We can just take the definition of no signaling and locality, and we know that in locality the probabilities are independent. The marginal probabilities are independent, and we can just plug that in the no signaling condition, and the no signaling condition will always be satisfied. But like, what about the converse? So does no signaling imply that the correlation has to be local, or is it possible that a correlation is both no signaling and non-local, or perhaps even better, genuinely non-local? So we talked about this correlation like a couple of times. This is called the Ardehali-Svetlichny correlation, and it is known like around 15-20 years ago that this correlation, or a game corresponding to this correlation, is actually both no signaling and generally non-local. So this cannot be simulated by any by any bipartition. And also, if the parties are sharing this correlation, they cannot use it to communicate. And moreover, we also know that locally we can simulate this correlation with probability 1/2 in the limit. And if we have like access to bilocal correlations, then we can simulate this probability with only 3/4. So now let us turn to the ideas, to the analogous ideas about causality. So we talked about locality, non-locality, and the no signaling, and is there any correlation that satisfies um, non-locality and no signaling. So now let us talk about the analogous ideas of causality. So let's first understand what is causality. So here's the notation we're going to use. um, we're going to use this fancy less than equal to say that a party is like something is happening in the past of something else. So in this diagram we see that we first spin this roller and we read the output. So spinning is happening before reading the output, so spin is in the past of read. And similarly, we can also say that read is in the future of spin. We again use this fancy greater than arrow. So what are causal orders? First, you define static causal orders. They are just like relative ordering of parties that the so we're saying that some parties in the like we define an order of parties, and like the parties coming first are like in the past of the parties coming later. So if we see a two-party example, we say that Alice is in like in the first we can have two orders. In the first order we have Alice is in the past of Bob, and the second order Alice is in the future of Bob. And for three parties we can have like any of the three factorial permutations of Alice, Bob, and Charlie, where like for example in the first case we say that Alice is in the past of Bob and Bob is in the past of Charlie. So there is kind of an order, a causal order in which they act. And again, like for n parties, we'll have n factorial permutations of causal order. But this is not enough to define causal order. Uh, like in the literature, we also allow dynamic causal orders. What do we mean by that? We say that that is the ordering of the parties, but the parties in the future, but the parties in the past are allowed to decide the order of the parties in the future. So in the two-party case, it doesn't change much because there are not too many parties. Like for example, Alice comes first, so Alice does not have anything like any order to change. There's only Bob to come. But if we look at the three-party example, and if we say that Alice will be the first party, then if you look at this correlation, the third one, sorry, like if you look at this causal order, it says that Alice comes first, and then if the input bit of Alice is 0, then she decides Bob to come second and Charlie to come third. But if her input bit is 1, then she decides Charlie to come next and then Bob to come in the end. Um, so you can see that that any static causal order is also dynamic causal order, because Alice can just simply ignore her input, but then she can say that like whatever the causal order which was decided initially will remain the same, and like all the parties will follow that causal order instead of she deciding whether she will change the causal order based on her input. So so this is like a more general case of the static causal order, and we even in if in some scenario, if this case occurs, we say that it is still a causal order. So there's an example like showing that the dynamic is strictly better than the static causal order. So if we define a game where we choose like m uniformly randomly between 1 to 3, and if m is equals to 1, Alice has to guess the XOR of the inputs of Bob and Charlie. And if m is equals to 2, Bob has to guess the XOR of the inputs of Charlie and Alice, and similarly for Charlie. So for this game, maybe you can guess the probability of winning of static causal order and dynamic causal order. Like first, let us look at the static causal order. The probability of winning here. So if you take a causal order, for example, if you say that Alice comes first, then Bob comes, then in the end Charlie comes. So in this case, the probability, yeah. So in this case, um, only Charlie will be able to guess whether um, uh, yeah. So if you have a particular causal order like Alice, Bob, and Charlie, only Charlie will be able to guess its output correctly, and Alice and Bob will not have like enough information to guess. So for example, if we look at Bob, Bob needs to know both z and x in order to guess z plus x, because otherwise, because parity is a sensitive function, and if Bob only has like the input bit of Alice, Bob will not be able to guess um, the parity of the input bits of Alice and Charlie correctly. So in both the other cases, the parties can only guess with probability one half. It's just a random output bit, and Charlie can also can guess it correctly because he has all the information that he needs to calculate x plus y in this particular causal order. But if you want to generalize, you can look at any causal order, and the same argument follows. So the probability of winning would be like 1/3 for Charlie, and for the other two parties, the Alice and Bob, and like if m is equals to 1 or 2, then they won't be able to guess with probability more than half. So the probability of winning is 2/3. But if you look at dynamic causal order, and again if you assume and again if you assume that Alice comes first, like without loss of generality, then if m is equals to 2 or 3, then Alice can decide whether Bob should come after Alice, or Charlie should come after Alice. So for example, if m is equals to 2, then Alice would want Bob to come in the end, because she would want Bob to know all the information. Yeah. Yeah. So for example, if m is equals to 2, Alice could say that Charlie comes first, like right after Alice, and then comes Bob. So that Bob has the information about z and x, and then Bob can correctly guess z plus x, and the parties win in that case. So with probability 2/3, like if in the case when Alice is first, um, if m is equals to 2 and 3, the parties can win perfectly. But if m is equals to 1, then Alice has no information about y and z, and the parties can only win with probably half. So this is the expression we get, and if we calculate this, we get 546. So causal correlations are just a convex mixture of correlations corresponding to different dynamic causal orders. So let's look at an example. So for the two-party case, we could say that either Alice could come first, and then so which means that Alice has only access to x to guess her output A, or to decide her output A, and Bob, since comes later, Bob knows the input and output of Alice and also its own input. So Bob knows x, y, and A, and then Bob can decide what is B based on those inputs, or based on those bits. And like we are seeing that this is a convex combination of the causal of the case where Alice comes first and the case where Bob comes first. So you can look at this expression, and in this case Bob is coming first, and then Alice is using the information that has occurred in the past of Alice to decide her output bit A. So we can have like a convex combination of these with probability P. Alice comes first with probability 1 minus P. Bob comes. And we say that a correlation is non-causal if it is not causal, similar to non-locality. So what is biocausality? We discussed biolocality, and the ideas in biocausality are similar. What we do is we partition the set of parties into two parts, P1 and P2, and we say that that the parties in P1 are allowed to communicate with each other, and similarly for the parties in P2, but all the parties in P1 must act before the parties in P2. So similarly, we can define the idea of bicausal correlations, in which we can say that the interpartition correlations must be causal, which means that the parties in P1 must act before parties in P2, while like there's no restriction on intrapartition correlations. And so here is again an example. 1473 are allowed to communicate with each other and like do whatever they would like to do, but they must act, but like all of them must act before, must produce an output before um, 2, 6, and 5, who are again allowed to communicate with each other. And so we discussed that every static causal order is a dynamic causal order. The parties coming earlier could just disregard their input in case n can say that they're not changing the causal order that was decided earlier, and then it remains as a static causal order. So every static causal order is a dynamic causal order. And we can also note that every dynamic causal order is a bicausal order, because we can define a partition. Um, so it, like even in a dynamic causal order, there's one party that will always come first, and let us denote that party by party k. And then we can define a partition in which P1 is the party K and P2 is like all of the other parties. And in this case, um, uh, so if you look at the definition of the dynamic causal order, the first party does not know anything. The first party is allowed to decide the causal order of the later parties, but the first party only knows their own input bit, right? So in this case, we can say the party K will only know its own input bit, uh, since it is in the partition P1, and the partition P2, and the parties in the partition P2 will know the input bits of all the other parties in the partition P2, as well as the input and outputs of the parties in P1, which is K. So the parties in partition P2 knows everything that they need to know in order to calculate their output. So this is again more general than the dynamic causal order. Let us now briefly talk about genuine non-causality, which is extremely important. So a correlation is generally non-causal if it is not bicausal, as was the case with bilocality and genuine non-locality. And here's an example of this. So in this case, you can look that the outputs of all the three parties are not dependent on their own inputs, but the inputs of the other parties. So for example, the output bit of Alice is dependent on the input bits of Bob and Charlie, and similarly for Bob and Charlie. So in this case, we cannot define two partitions such that they act causally, and we are always able to produce the outputs that are stated here. So you can like verify this, or you can just check this by like trying to design partitions P1 and P2 such that they act causally, and you are still not able to win this game, let's say. Since for all the three parties, the outputs are dependent on the inputs of the other two parties. Um, and now we look at the most general setting that we have been looking at, right? Like for now. So if we say that every party is allowed, if there are like multiple parties and every party is allowed to have to do some local operations on their input and output, and but they're also allowed one more thing, that is they can interact with something called an environment, which we want to be logically consistent. We discuss these ideas next. So the framework is as follows. If you have just a single party, let's call it S, and the party is getting an input X and will have to produce an output A. But the party can also decide to interact with the environment. It can produce an output O, which she can give to the environment, and then the environment can do some computation which has to be logically consistent. We see what logical consistent means a bit later. And the environment will produce an output which we denote by I, which the environment will transfer to the party S, and then the party S can use the I to produce an output A. So in general, the parties are allowed to interact with the environment, but not with each other. So in the general setting, we have this sort of framework that each of the parties are getting an input X naught, and then they're allowed to have some communication with the environment using O's and I's. Um, and then they can decide based on the output of the environment and also X and also O to decide like what is A naught. For example, for the zeroth party. But in this setting, we might have okay. So let's first discuss like what are the associated probabilities of each of the things at play. So, for example, if you have environment, the environment is getting I input. The environment is getting O input. The environment is getting n input bits, namely O not to On minus one, and the environment is producing n output bits, namely I naught to in minus one, up to in minus one. So the environment gets like O vector and produces the I vector. For the jth party, well, you can notice that the jth party receives xj as the input, and also ij as the input from the environment, and the jth party produces aj and oj as we have stated here. And the overall in the overall case, um, the parties are getting x as the input, and the whole setup is generating um, first O, then I generated by the environment, and then A again generated by the parties. So in the whole setup, only X is given, and the parties and environment together are generating A, I, and O in the given setting. But if you look at but if you say that that you do not put any restrictions on the environment, then it may be possible that you are able to derive some contradictions. So there is a very well-known contradiction known as the grandfather antinomy. In which case, if we say that the environment um, on getting O is just producing I as O, so the environment always produces I, which is equal to the input O, and we say that, and we can also like if we are allowed to have general local operations of the parties, then we can say that the parties are allowed to use any of the input bits, and they can produce the output bits A and O. So we can say that O in particular is equal to I plus one, which is like the negation of I, and I is coming from the environment to the parties. So in this case, you can look easily that there's a contradiction because I has to be equal to O, which has to be equal to I plus one, and I is equal to its own negation. So there is directly a contradiction. This is known as the grandfather antinomy, because there's a very very famous grandfather paradox. Um, I encourage you to look at that. Um, it 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 like proves that we cannot have time travel in the most general setting. And so there's also an information antinomy. So this is a bit subtle. In this case, this is extremely similar to the grandfather antinomy. Other than that the party is producing O to be equal to I. So the parties are saying that so the environment will produce I, which is equal to O, its own input, and the parties will produce a O, which is equal to I. So where is the contradiction? I is equal to and O is equal to I. So we have I equals to I. Where is the contradiction? But the contradiction is in assigning the values to these variables. So we have not been able to assign like any value to I. So we can say that I is equal to one, and we can also say that I can also be equal to zero. So there's a contradiction there, like because these are not well defined. We don't know what I is, so we can assign any of the values 0 or 1 to I, and so then there can be a contradiction. And it was recently proved like last year, the grandfather antinomy is locally equivalent to the information antinomy. um, so what do we mean by logical consistency? How do we enforce logical consistency? We just say that the probabilities are well defined, and if the probabilities are well defined, the correlations we achieve has to be logically consistent. Because if you look at it in the last two examples, the grandfather antinomy and the information antinomy, the probabilities were not well defined. And so if we have the probabilities to be well defined, then we cannot have any contradiction. So that's by definition logical consistency. Now we look at the connection between the two. What is like, how are these things related, non-causality or causality and logical consistency? Well, we can easily see that every causal correlation is logically consistent, because you can generate an environment which is logically consistent. So you could just say that if you have the causal order Alice, Bob, Charlie, um, and so on. So so Alice can give its input bit to the environment, and the environment can calculate X for Alice and like give it to Alice, and then the Bob can give its input bit to environment, but the environment already knows the input and output of Alice, and so Bob, and so the environment can use the input and output bits of Alice and also the input bit of Bob to calculate the output bit of Bob, and then likewise this probability like this probability distribution is well defined, and so every causal correlation is logically consistent. Like what about the converse? Does logical consistency imply that every correlation has to be causal? Well, I guess like similar to the case of non-locality, it's the answer is no. So this means that there can exist a logically consistent correlation which is generally non-causal. And so this is where our contribution comes in. So inspired by the Ardehali-Svetlichny correlation, we define the correlation, which is as follows. So we say that again, this is um, the XOR of the pairs of n's of all the parties I and j. And so this first term you may remember from Ardehali-Svetlichny correlation, but we also XOR it with some other term, and which is a little bit complex to understand. But like, what's the intuition behind it? So the so if we see that if lambda I is equal to 1, then we have these single terms of the parties of the other parties other than the party k, and and like when is this and like when is this the case? It happens when like if I is less than k, then then xi is here only when the parity of I and k are equal. So this operation is the mod 2 operation. This means that I is equal to I is equal to k mod 2. And similarly, if I is greater than k, then we say that if the parities of I and k are different, then we have these single terms. So if you look at this diagram, we're just simply saying that if we just remove the kth party, if we put it into trash, we'll have alternate terms of whether we are having the input to that party in our output term, or we are not having the input party. So since we are putting we are trashing the kth input bit, that is xk, we are just simply aligning all the input bits, and since we do not change the order and since we do not change the label of all the of all the inputs that are being trashed, like aligning all the input bits, and then we are saying that we are choosing those which are like alternate, uh, like we're choosing each of the input terms alternatively, and we show that this correlation is logically consistent. We just say that um, that if the parties are given xk, uh, the party will give will like transfer xk to the environment to get ok, and the environment will calculate ik for the parties which the parties will output as their output ak, and like the non-trivial step in this um, and like the non-trivial step to show that this is logically consistent is to show that the operation of the environment that is given OKs, how is the environment producing IK. So we also show that this is logically consistent in our paper. If someone is interested, we can share it with them. And also we also show that this correlation is bicausally hard, which means that in the limit, if we are allowed only bicausal correlations, that we can simulate this function with probability only 1/2 in the limit. And this follows directly from the hardness of the Ardehali-Svetlichny correlation, which is known from like many years ago. And we can also note that every correlation can only be simulated with probability, can be simulated with probability at least one half. If we are allowed like bicausal correlation, if we are allowed access to bicausality, then we can simulate any correlation with probability one half. We can just let the zeroth party to be in the first partition, and all of the other parties to be in the second partition, and we can uh, and like since there's only one party in the zeroth partition, that party only has to guess like one input, like their own output bit, which is a naught, right? And since we have binary inputs and outputs, a naught can only be 0 or 1. And if the and this means that the zeroth party can guess a naught with probability at least half. And the parties in the partition 2, since they occur causally later, they have all the information about the partition P1 and also the partition P2, and they have all the information they need to know to not make a mistake. So only the zeroth party can make a mistake, and that is still with probability less than half. So we can always win any given game, or we can always simulate any given correlation with probability at least one half by causally. And so this is like the this was and like we actually showed that the set of logically consistent correlation is infinitely larger than the set of causally or even bicausally simulatable correlations. And um, so there are some things to consider for future. We talked about classical logically consistent correlations, but there's also a notion of quantum logically consistent correlations, which is known as the process matrix correlations. So if we allow for those correlations, then is the set of classical logical consistent correlations included in the set of quantum correlations, or are they equal? We don't know this yet. And also, we did not answer like whether there can exist a correlation, a logical consistent correlation, which can simulate it causally with probability only 0. Our correlation was able to simulate. Our correlation can be simulated causally with probability one fourth. We Although we do not talk about that, but we don't know yet that there exists a logical consistent correlation which can only be simulated causally with probability 0 in the limit. And so again, there's also another question that what natural principle implies no violation of causal order? Does there exist any principle um, using which we can have like causal order, or we can have like no violation of causal order? And also, this is again a very like a non-trivial but extremely important question, that if we have the set of non-causal classical computation, is it equivalent to having quantum computation? So if we allow for non-causality, and if you have a if you have a model of classical computation, is it equivalent to a model of quantum computation? Well, we don't know yet. And this is the end of my presentation. Thank you for being here. Are there any questions? So maybe Gibran, you can take it from here.
Thank you. Thank you, Amin, for the talk. There are a couple of questions that we've written down based on registration. So we'll just go through them first, and then there were a couple of questions in the chat window. So the first question is essentially asking, how is this work related to quantum computing? Amin, you're mute.
Oh, sorry. So basically, the set of non-local correlations, as we discussed earlier, are like a superset of the set of quantum correlations. So every quantum correlation is a non-local correlation. Um, but but there are correlations which are non-local, and we cannot simulate it quantumly. So we are kind of like generalizing the idea of non-local correlation. And I also discussed this idea of whether if we have like non-causal correlations, and if we have a computation model based on that, so is that equivalent to doing quantum computation? Well, um, I guess it may be, but we do not have any hints to even answer that question. So this is an open question.
Right. The next question is how quantum communication could benefit from non-locality?
Um, so, so if you have access to perfectly non-local boxes, then it is known by a result from Win Van Dam that that we can simulate any function, that we can calculate any function, any distributed function with only one bit of communication. But if we have like noisy non-local correlations, which are quantum correlations, we can still benefit in our calculation of functions, but we don't really know that we, I guess, so we can still reduce our communication. I'm not really sure by how much.
Okay. And one of the chat window questions was, what do you really mean by correlation in this talk? Correlation here means total correlation, quantum and classical for both, as in mutual information.
So what do you mean by total correlations?
I assume it means basically defined over the entire sample space.
Oh, so the idea is like if there are like multiple parties, and by correlation we mean that there is a resource that they are sharing, and because of the resource, because of that resource they're sharing, their outputs are correlated somehow. So this is the general notion of correlation that we have used. And what else was there?
So is the notion of correlation kind of related to mutual information?
Mm, well, yes, kind of. Yeah, because mutual information is actually like is like in other words can also be like known as the amount of information shared by both the parties. So well, yes, you can calculate mutual information of correlations, and those are bound to be more than those um, and, and those are bound to be higher than those of no on those of non-correlations, of which where the parties are not correlated at all. So it is somehow related. I guess it's the same thing.
Okay. So this is a question when you were explaining the example with the all-to-one signaling slide. And the question was, in that specific calculation that you're doing, where does the factor of half come from? So I'll stop sharing the screen and maybe you can put up the slide.
Sure. This one.
Yeah,
And like, what was the question? Where does the half come from?
yeah.
So the so for example, if Alice is first and Alice doesn't know Y or Z or like both, uh, but Alice can still guess some output bit which can be 0 or 1, and her guess could be correct with probability half. She doesn't know if it will always be correct, if it is equal to Y plus Z, but since Y plus Z is equal to either 0 or 1, she can just simply guess, like make a random guess 0 or 1, and it may be correct half of the times, and it will not be correct half of the times because the inputs are uniformly distributed.
Um, Again, follow-up questions from Moise. Can you give an example of logically consistent and well-defined probability?
Well, logical consistent correlations are by definition well defined. So if we have a well defined probability distribution, we call it logically consistent. That is by definition.
And then the other one is more of a statement that the mathematics involved must involve conditional probabilities and entropies in the literature. Would you agree?
Um, well, there are some connections made between information theory and non-locality, but like in the literature of non-locality as such, it is not required to like have mutual information or like something from information theory. But there are definitely papers which concern the connections between non-locality and information theory. There are many like and there are like many papers of that of this sort because these ideas are very related.
Um, and the next one is, you mentioned interaction with the environment. Is the nature of the interaction weak interaction with the environment? And if yes, then will the dynamics of the parties be within Markovian regime, or are there exceptions?
Well, I don't. Well, this is a very nice question. I don't know if I can answer this fully. But like in our case, what we're saying is that the parties are allowed to the parties are allowed to communicate with the environment as such that the power distributions of the parties and of the environment does not produce a contradiction. So the parties are allowed to have any sort of communication with the environment as long as it does not result in a contradiction.
I guess what you can also add is that in
And
the work that you've presented, it's just we are communicating classically with the environment. And what is being presented as future
yeah,
work is the possibility of what happens when there's quantum communication with the environment.
yeah, yeah. So the idea is like there can only be like a one bit of input sharing with the environment, and this is deterministic classical communication with the environment. So we can generalize it to quantum communication. We can also further generalize it to communicating probability distributions with the environment. Um, so this can also be generalized further, but like in all we had in today's presentation, like the setting of the environment was the most general one.
Okay. And I guess the last question that we have on the chat window is going back to the probability calculation. In addition to the half, the question is also about the 3/4. I guess the argument is very similar.
Where?
So exactly going back to the probability calculation in the example. Yeah, that one.
Of which example?
The alt
This
one.
one?
Yeah.
Yes. What is the
So
question?
in the author, so this is asking, where do we get the half and 3/4 from the probabilities when talking about bilocality on the non-local no signaling slide? Sorry, this was another slide.
This one, yeah. So we don't prove this. We are just stating this result. But if you think about it, um, well, if you think about this function on the right hand side, um, uh, yeah. So then you can explicitly calculate how many number of zeros are there and how many number of ones are there in this function in the output bits of the function, like how many input instances are there such that the output is 0, how many input instances are there such that the output is 1. Well, you'll see in the limit that goes to half. So if you have no information about um, about x about the input of all the other parties, then you can only guess this function locally with probability 1/2. And are also buy local strategies which can let you achieve 3/4, which is the optimal, but we don't show it here. It's not a trivial argument. It's a bit nuanced, and yeah, it is there in the papers. If you want me, I can share it with you.
I think that's all the questions. Thank you again, Amin. Wonderful talk. And thank you to the audience. If there are no additional questions, then I'll think we'll close the session. I'll just kind of give it a few minutes in case there are
Thank
questions.
you. Thank you so much for being here.
Thank you, Amin. Thank you, everyone. Goodbye.